Okay, we are very happy to have back once again Mateusz Łewyk, who will speak from the University of Warsaw, who's here to speak on simplest model properties for piano arithmetic on a question of Montalban and Rossegger. Go ahead, Mateusz.
Yeah, thank you very much. Thank you very much for your invitation. I'm very happy to be here. So actually, my interest in this topic, it has much longer history than just this particular result. So I've first heard about Scott's rank and Scott's style analysis during, I think, Matthew Harrison's trainer lecture on logic colloquium. And then I guess jointly with Leszek, we started computing some Scott's rank of some prominent classes of models of PA. Then I forgot about it. And then the topic went back to me thanks to Antoni Montalban and Dino Rossegger, who started Scott's style analysis for Peano arithmetic, and then raised some interesting questions, which we were able to solve jointly with my student. And this is his name. So this is joint work with Patrick Szlufik. And this talk is about two main characters, PA and the infinitary language L omega 1 omega. So in the philosophy books, in the formal philosophy, for example, mathematic truth theories, when you do the introduction, we normally spend a lot of time explaining what is PA. And then we say things like, oh, and we assume some background in Gödel's coding, and that's routine. So I guess I don't have to explain what PA is. Now I will start explaining what is L omega 1 omega and how it is stratified. So what is Scott's analysis? So formulae of L omega 1 omega are generated from literals, which means atomic and negated atomic formulae, by adding the universal and external quantifiers and taking countable conjunctions and disjunctions over, as I said, countable sets of formulae which have finitely many free variables, which means that in the resulting formula there are finitely many free variables. So we do not include the negation. We have all the duals in the, you didn't take in the compound formulae. You don't add negations, as can negate formulae in a De Morgan fashion. So these formulae of this language, they are naturally assigned ranks based essentially on the number of alternations of disjunctions and universal quantifiers with disjunctions and exponential quantifiers and conjunctions and universal quantifiers. So here's the definition. So sigma 0, pi 0 infinitary formulae. These are all quantifier-free formulae of first-order logic, so finitary formulae. Then the sigma alpha formulae, they are all formulae of the form disjunction over a countable set of formulae of the form exists xi phi, where phi's, they are in some pi beta for beta less than alpha, and dually for pi alpha. So, by the way, if you have any questions regarding this, then please ask them. If not, I assume that this
Mateusz, I do have a question.
Right.
Can you remind me how this is quantified? So does the beta have to work for all I at once, or is it okay? So if you have a disjunction of formulas of rank n,
for every I, there is some beta less than alpha.
Okay, so if you have a disjunction of formulas whose ranks range over the natural numbers, that's sigma infinity omega.
That's sigma infinity
okay,
omega. Yeah. And that's the only way of getting of doing the. I mean, this and the infinite conjunction to perform an like infinite jump. Roman, do you have a question?
So there are no finite ranks?
No, there are finite ranks. So if you have just, you can repeat.
Oh, so the finite ranks, I see. So if they're all of bounded, if they're all first order of bounded complexity, then those disjunctions and conjunctions also will be of finite ranks. Okay.
Yep. And one general remark: we shall always work over relational signatures. This is slightly artificial in the case of Peano arithmetic, but we can just assume that addition and multiplication, they are ternary predicate, successor is a binary predicate, and we have just axioms asserting that they are total functions, and so on in the usual way. This is just to keep it uniform between various kinds of theories. Right. So maybe let me write oops, sorry. Sorry, I think I will use a different program for slideshows because something strange has happened. Okay, I want to quit that. And then if I okay, so that's unfortunate. Okay, sorry, let me try a different program to show the slides. Okay, just like
so Mateusz, I'm sorry. So what would be an example of a sigma 2 formula or a sigma 1?
So for example, this is a very good question. So for example, you can have the nth successor of 0. For example, this is naturally expressed as a sigma 1 formula with a constant and a bunch of existential quantifiers.
Right. No, so I'm still confused. So first order formulae don't have rank.
Oh, they do.
No,
I think any purely existential formula is going to be sigma 1, and a disjunction of purely existential first order formulas remains sigma 1.
Remains sigma 1, yep. Their conjunction becomes pi 2, for example.
Oh, I see.
Yeah, there's no restriction that these
there
pi
has
i's are yeah, I mean it doesn't, it's just existential and then closure under these disjunctions.
That's right. All right, I see. Okay, sorry.
Yep. Okay, so let's continue. Okay, so what is, for example, an example of a sigma 2 formula which expresses something non-trivial? So you can say that, for example, there is an I in omega such that X is equal to sorry. Such that there exists X0 such that S of 0 X0 right, sorry, I will write it differently. There is X0, there exists Xi, oops, sorry, that's slightly bigger, so that x0 is the successor of 0, and s of xi minus 1 is a successor of xi, and x is a successor, sorry. These are the successors, 0, 0, and 0. And x is a successor of xi, right? And this, so this is finitary quantifier free formula, right? So this is sigma 0, this is sigma 1, and this is the conjunction over sigma 1 formula, so still sigma 1. Okay. Assume it's fine. Okay. So this ranking of formulae gives us a natural stratification of our complexity measure on models for a given language or for a given theory. So let me explain it. So first of all, there is a classical result due to Scott that each countable structure can be characterized after isomorphism by an L omega 1 omega sentence. As such phi, and such phi is called Scott sentence of this model. So this gives rise to a parameterless Scott rank of a model. So the Scott rank of a countable model M, denoted SR of M, is the least alpha such that there is a pi infinitary alpha plus 1 Scott sentence for M. Okay, in the next slide I will explain why we're taking pi and why alpha plus 1. This is just, it turns out that this is the right notion, that this is the right way to do it, because various other characterizations. And also this gives rise to the notion of the Scott spectrum of the theory. So the Scott spectrum of the theory T is just the collection of ordinal numbers such that which are Scott's rank of some models of T. Okay. Here we're taking just countable models, and you can assume that I will refer only to countable models in the throughout this talk. So in fact, to give like perhaps an example, so omega categorical theories like DLO, for example, linear order, they have just the Scott spectrum is just a singleton. And for PA, we will see shortly what it is. Right. So now, why pi alpha plus 1? So it turns out that this notion of rank is very robust, and we have the following equivalent condition. So we have a countable structure and any ordinal alpha, then this alpha, there is a pi infinitary alpha plus 1 Scott sentence for M. This is equivalent to the fact that each automorphism orbit in M as a subset of M is infinitary sigma alpha definable without parameters. So this is perhaps a point to remember where you have just the same alpha. So in particular, a Scott rank of a model is the least alpha such that each automorphism orbit of this model M is infinitary sigma alpha definable without parameters. And this will be, by the way, the parameterless definability will be our usual. I will talk mostly about this parameterless definability until the end. At the end, I will go back to say something about parameterized Scott-Rank. Okay. So there is yes.
But also, whose theorem is that?
Yeah, that's a good point. So it seems that
and the follow-up to it. So for example, because I'm thinking, what happens when M has no automorphisms? So there are no orbits, just points. So
so you mean that automorphism, the orbits are singletons, right?
Right. So is it Scott's theorem, or this is something new?
I think no. This is so good point. So the history, as far as I know, is that essentially the implication from 2 to 1. This is due to Scott, and this is how this theorem from the previous slide was proven.
Mm-hmm.
That you first define all the automorphic orbits, and then collect them all together into a single sentence, and saying that essentially there are this many elements in this automorphic orbits and this many elements in this automorphic orbit, and you do it. So thank you very much, Roman, for this question. You do it for all, not just for orbits of single elements, but for orbits of all tuples, of all finite tuples of elements. So each automorphic orbit of each tuple in M is sigma infinity alpha definable. Okay, and the implication from 2 to 1 is due to Antonio Montalban, who actually showed also how to connect all these notions that I will be talking about in this list. So perhaps some of the implications, they were known before, but I think that the final touch is due to Antonio Montalban. Yep. So there is a connotation with the descriptive set theory. So this is equivalent to set presentations of M being pi0, boldface pi0 alpha plus 1 in the Borel hierarchy, and M being uniformly delta 0 alpha categorical, which roughly means that given 2 copies of M, it takes at least alpha many, at most alpha many jumps in these 2 copies to compute the automorphism. This is boldface, so with a parameter. So this is just I'm citing this result to witness that this is like this seems to be a good notion. So it's pretty stable. And there are also interesting connotations to computability, to model theory, and descriptive set theory. Right, so let me continue. So now, using this theorem and these definitions from the previous slides, let's compute some easy Scott's rank ranks for models of PA. So the Scott's rank of the standard model is 1, because each automorphism orbit is sigma 1 definable. Right, so we essentially say that the first guy from this tuple can be reached in n many steps, is the nth successor of 0, the second guy is the kth successor of 0, and so on. Right? So let's go further. So in more general, if M is a prime model of PA, so a model in which every element is definable with infinitary first order formula, then the Scott rank is less than omega, because each automorphism less than or equal to omega, because each automorphism orbit, so the orbits, they are just singletons, and each each such point is definable with first order formulae, right? So less than, in particular, every such orbit is definable with a sigma, with infinitary sigma omega formula. Okay. So what's next? So then countable and recursively saturated models. And in general, I think all homogeneous models of PA. They have rank smaller or equal to omega plus 1, because each automorphism orbit is defined by the type of the elements of this orbit. Right? In a countable and recursive saturated model, if two elements, they have the same type, then you can move it, then you can find an automorphism which maps one to the other. So they are in the same automorphism orbit. And you can write first order type of an element as a pi omega, infinitary pi omega formula. So it's sigma omega plus 1. Okay. Are there any questions? Okay. If not, then I will continue. Right. So what we know, so Scott's analysis was typically done for like more model theoretical algebraic theories like linear orders, and for the first time, I think that, I mean, there were some results due to, for example, Roman and Koski, also which were about the complexity of the isomorphism problem for models of PA, which gives an information about models, about the Scott spectrum of PA. However, the first, like, more detailed Scott analysis of PA was done by Montalban and Rossegger. What they proved is that if you have any completion of PA, then the Scott spectrum of this, sorry, so this is, so there should be th of n in this. So the Scott spectrum of the standard model, this is just of the theory of the standard model. This is 1 and all ordinals from starting from omega plus 1 up until omega 1. So there should be also omega plus 1. Here I just put it wrongly. Right, and this is th of n. Right, and then if you have a non-standard completion of PA, then its Scott spectrum is omega, they are all infinite ordinal numbers up to omega 1. And the proof of it uses Geifman minimal types. They essentially find a way to interpret linear orders in models of PA, and then copy the result from what is known about linear orders. And Dino was talking about this here at MOPA, I guess last year or 2 years ago. I forgot when it was exactly. So let me point to an interesting phenomenon here, which was observed by Darek Karocinski. So we say that T has the simplest model property if there is the unique model of T of the least Scott rank, right? So we look at models with the least possible Scott rank. If there is just one such model, then we say that this theory has the simplest model property. And the corollary is that PA has the simplest model property because its simplest model is the standard model. However, to give a non-example, for example, if you have PA plus non-con PA, then this theory does not have a simplest model because all prime models, all non-standard prime models will be, sorry, let me put it the other way around. So this theory obviously does not have a standard model. So by point 2 in this theorem, its models are of rank at least omega, right? And actually, from what we saw in the previous slide, so each prime model will have each prime model for any extension of this theory will have a Scott rank exactly omega, and there will be just continuing many such models, right? So maybe summarizing this theorem from what we learned from the previous slide, it follows from the analysis of Montalban and Rossegger that all non-standard prime models, they have ranks exactly omega. And moreover, a stronger fact is true due to the fact that actually PA can formalize the back and forth relations, partial truth predicates, or from the other perspective, partial truth predicates. Each non-standard model of PA will have rank at least omega. Right. Are there any questions?
Sorry, can you say that again? Why do all non-standard models have rank at least omega?
So that we'll see. Actually, we'll see. I will outline the proof in a few slides because with Patrick, we actually generalized one observation from this paper. But this is also essentially due to the fact that Scott's rank, okay, you will see it in one of the next slides. Right. So what they actually raise, there's an interesting questions. So what can be said about? Let me erase this. So the notion of Scott rank gives us the possibility of gives us notion of layers of models of PA, and we can ask, can a given layer, so for example models of Scott rank alpha, can they be characterized by some joint model theoretical property, right? So the general question that we find interesting is that given alpha, what is the set of models of PA of Scott rank exactly alpha from the model theoretical perspective? What can be said about it? More concretely, they ask whether there is a non-atomic homogeneous model of PA of rank omega. So in particular, is it true that sorry, but non-atomic in this context, this is just not non-prime in the context of PA. And so this is equivalent actually to the question whether whether the models of PA of rank exactly omega, they are exactly the prime models of PA, or there are more of them. Right? So the question, the answer that we found is actually to this concrete question, no. So the non-standard models of PA of rank omega are exactly the prime models. So turns out that this also computability theoretic characterization via Scott rank. So by Scott rank, it just filters out exactly the prime models of PA. And let me draw an immediate corollary. So not only PA has the simplest model property, but also each completion of PA enjoys the simplest model property, because it turns out that if you take from this theorem that I will prove in a second, it follows that if you take an arbitrary completion of PA, then the prime model of its completion is the least model, is the least model of Scott is the simplest, is the unique simplest model for this completion. The unique model with the least Scott's rank. Okay. If there are no questions, then let me. Now I would like to just go to the proof of this theorem. Okay. So let me start by showing you the strategy. So we first assume that there is an undefinable element in M. However, Scott's rank of M is omega, and we will arrive at a contradiction. So let alpha be this non-definable element in M, and by the assumption the orbit of A is infinitary sigma omega definable, because the Scott rank of this model is omega, so each orbit is sigma omega definable. Okay. However, what it means is that actually for some n, this orbit must be infinitary sigma n definable. Why? Because if a guy from this orbit, for example A, if it satisfies this infinitary disjunction of formulae of complexity of infinitary sigma n, then it satisfies one of them. But then since this is an orbit, then each guy in this orbit must satisfy this formula, this sigma n formula. However, no guy from outside the orbit can satisfy it, because then it will satisfy the disjunction. Okay. So what we have to take care of is, now we arrive at the conclusion that in this model, for some n, this orbit of this undefinable element is infinitary sigma n definable. And now we'll get rid, in this context, of infinite conjunctions and disjunctions. Right? And for this, let me just introduce a correction. So I think that for trivial reasons, perhaps no, I think that this is actually true. What we'll need actually later on is the direction left to right. So why I hesitated is that, for example, I mean, prima facie, these infinitary sigma and formulae are not closed under finite conjunctions. However, I think that you can always push them inside over via De Morgan laws over an infinitary disjunction, finally hitting the level of atomic formulae where it can stay. So let me focus on the implication right to left, which we actually will need. So if finitary type sigma and finitary type of A is the same as finitary type of B, then their infinitary types are the same. Okay, and why in an arbitrary model of PA, why this is so? So this follows because this notion can be so this equality can be characterized by a game, and this is like this game like formalizes back and forth proof of the like that it is possible to send A to B. So how this game looks like. So first, player one who wants to disprove this. So this works for general infinitary sigma and alpha types. There are two players, 1 and 2. So first, so player one wants to disprove this claim. And you can, okay, so once again, so think of it as the game which takes place between two structures, M and A, and M and B. And first player one chooses one of the structures. And then he selects an ordinal beta less than alpha, and adds to A or B. Say that he has chosen this structure. Adds a new element. Then player two responds. So maybe let me call it A1. A1. Then player two responds with an element from a different structure. This is M B. He chooses some B1. And then in the next round, the two we switch the role of these structures, right? So now player one selects one more ordinal, say beta 2, strictly smaller than the previously chosen one, and now an element from this, so B2, and the second player responds with an element from the first structure, say A2. And the game continues until we hit 0, and then we check whether the atomic types of both tuples, which were formed during this game, have the same quantifier-free type. Okay, and this characterizes the equality between infinitary sigma alpha types, right? So if we live in the model of PA and have to deal just with sigma n types, then we can use the strategy from the usual back and forth argument, for example, between countable and recursively saturated models, because sigma n types, which are realized, they are coded, and coded sigma n types, they are realized. So in this way, we can always find a strategy for player two, which essentially say, play the element with the same type of the same type with respect to finitely many elements that were chosen before. So shall I say more, or is it roughly clear what how the proof of it looks like. This is the implication right to left.
I think it's good.
Atar? Okay.
Yeah.
Good.
Thanks.
So, and essentially, so Atar, if you use this fact, then you will learn that that actually non-standard models of PA, they cannot have rank less than omega. I would have to think slightly more about the proof, but this is a key fact, a key step in this proof. Okay, so let me erase this. Good. Right. So what is now my claim? So I claim that I can find B in M, which has the same sigma n type as A, but different full type than A, which would obviously contradict what we had before, right? Why? Because if B has the same sigma n type as A, then by the previous lemma, it has the same infinitary sigma n type. Hence, by our assumption, it has to be in the same automorphic orbit as A, and hence it has to have the same type, the same full type. Okay, so I'm using just the implication right to left from the previous lemma. If B has the same sigma n type as A, then has the same infinitary sigma n type, then by our assumption they are in the same orbit, so their full types must be the same. Okay, so by what I think is the canonical use of the Ehrenfeucht lemma, sorry for the typo, it is enough to find a B in the submodel generated from A, to take all elements which are definable in M from this A, and this B needs to be different than A, but has had the same sigma n type as A. Right? So the Ehrenfeucht lemma tells us that in such a scenario, such a B will be definable from A, and hence will have different type than A by the Ehrenfeucht lemma, and then we just use elementarity between M and K of A, and this does the job. Okay, so now at this point, I think that this is essentially an exercise in overspill. So we first pick C in K of A, which codes sigma n type of A. This can be done. And since A is not definable in K of A, then for any natural number K, we know that there exists an X which is different from A, so that for every formula phi less than K, it satisfies if X satisfies phi. So X satisfies phi if and only if A satisfies phi. In other words, for every K, we can find an element which satisfies the same formula of Gödel codes less than K as A, because A is not definable. Right? And so by overspill, we can get an element which satisfies the same sigma n formulae as A, and it is different from A, and that's it. Roman, do you have a question?
Well, one has to be careful with muting and unmuting, but yes, I have a question. So it's look, so what I'm a little confused about the argument is that n for each of these results, like this page and the previous one, seems to be fixed. It could have been 1.
Yep.
Right. So
Yep,
so
that's it. But okay, so so it is okay. So the point is that
I see. But you choose that m for which
for
the
A,
right.
it is fixed
right,
for the orbit.
So you have to choose n accordingly to the definition of the new element. I see. And then from that point on, it's fixed, and then you follow the argument. All right. Thanks.
Yeah. So the point that this sigma omega definability, this is really weak, right? So if you just fix subset which is sigma omega definable, it will be infinitary sigma n definable. Right. So then one more observation, and this observation is actually something that I observed that I made while preparing to this lecture. So I'm not calling this a theorem because it's not properly verified, but it seems that if you are interested in the parameterized Scots rank, for many of us this is perhaps a more natural notion. The parameterized Scots rank allows you to fix finitely many parameters from your model, and then find the characterization of this model with these additional parameters, right? So in particular, with this notion, each finitely generated model of PA, each K of A, has Scots rank, parameterized Scots rank omega, because you can fix the generator and say that every element is definable from this A. Yeah, and then perhaps yeah, let me think whether you don't have to perhaps to also describe the type of this A. Okay, so perhaps this is not so easy. So because you don't have just, it's not enough just to fix A, but perhaps you should also describe the type of it. No, sorry, that's not true. So you can fix this element to generate this, and then you will have actually each orbit will be sigma infinitary omega definable with these parameters, right? And if you run this argument once again, and then you can show that actually every model of PA which is not finitely generated cannot have parameterized Scots rank omega, right? So essentially the same argument will do the job. So my claim now is that if you would like to have a parameterized Scots rank, the models of rank omega will be precisely finitely generated models of PA, which I think is a nice characterization. And that's it for today. Thanks a lot.
Let's thank our speaker. You can unmute or just put up your emoji. And let me take a look to see if there are questions. Feel free to unmute and then and go ahead.
Well, Mateusz, I just have one comment here about this parameter. The idea of the simplest model of a theory, T, that in this sort of, well, some kind of mathematical thing, what is the simplest model? If you look at an arbitrary completion of PA, it's a complete theory which is essentially the same as an set theoretic object as its prime model. The theory already has the names for all the definable elements, and the model is made of those definable elements, and the theory knows how each definable element is related to any other definable element. So in the sense, there is no difference between the theory and its model. Like you could say, I completely agree that the standard model is much simpler than the theory of the standard model, because it's just a set of natural numbers. So it's the simplest model of true arithmetic. But in this case, the theory and its simplest model are the same thing. The more complex the theory, the more complex the model, and vice versa. So I do not object to it, but I think this is misleading to call it the simplest model property in a sense in the case of completions of PA. And there is something also I want to mention here, that for finitely generated models, the idea of what's simplest and what's not is that also kind of vague, because every countable model has an elementary extension that's finitely generated. So in a sense, you have this finitely generated model of, it's interesting that it's of lower parameterized Scott rank, but it already contains any other model, not any other model, but you can start with a recursively saturated model of arbitrary complexity and have an elementary extension. So first order theory will be the same, and it will be finitely generated. So you would think it would be simpler because it has a small thread, but this parameter already codes so much that it's simpler with respect to the parameter, essentially codes whatever happened before. So I'm just saying that maybe the terminology could be a little bit adjusted, that the simplest will not always quite apply.
Well, so I would say that in the case we have a finitely generated model, then in the case, I mean, perhaps it is structurally quite simple, right? So we have just one element which sort of controls all the other ones, right?
But I think the word just doesn't apply. It's one element that already has all information about the previous structure. So it's not just one element, but equipped, it's so much, it's coded, the model knows so much, the theory of the type of this element.
Yep. Okay. Now
right. So
that's really the point here. Your point.
Yeah.
Yeah. I would also think more about. I mean, so actually, I mean, this is also a part of what we are interested in. So there is an idea of the simplicity behind these notions, and the lower the Scott rank, the model should be the model should be simpler. So perhaps what you say is that this is a wrongly chosen format for modeling this kind of situation.
Yeah, right. So my only comment here is right. So that once you allow parameters, and this is arithmetic, that arithmetic in the non-standard version can code so much into a single parameter that what you're saying is true, but this is what PA can do. So that, like in set theory, everything is a single set. But no matter how complex, and you still have some other. You have to apply some other measures of complexity to find out what's complex and what's, to have some kind of hierarchy of complexity. Now, and in the case of these of countable models, this really ruins the picture that you can have as complex model as you want, and now you have an elementary extension that's just coded by a single element, essentially. So that's kind of strange.
Yeah, I mean, as I've said, I'll have to, I think more about before I will defend this this intuition. That's, I mean, so to me, this is still like, so perhaps this is too coarse. This is too coarse grained, right? So too many situations, they are they are just equated by this example of finitely generated models, right? However, I mean, what I do like about this, that this is kind of a notion of simplicity that applies across the theory. So this is not like peculiar to arithmetic, to set theory, to sequential theories. So you can just take any theory whatsoever and ask whether it has the simplest model. And then also, for example, then narrow your attention to sequential theories and then ask, so which devices, which axioms, which kind of axiom they are responsible for having this simplest, for the theory having the simplest model. So in particular for I think that for example, for subsystems of PA, this is obviously like induction, which is responsible for this gap between the standard model and the next models in the spectrum, right? So you can, for example, if you take I sigma n, then what I think you can show is that the models of the next model after the standard one of the least rank, it has rank exactly n plus 1, and these are the sigma n plus 1 definable elements in a given model of PA, right? So in a sense, this the amount of induction in this case is partially responsible for say PA having the simplest model, and yeah, and similarly, I think that for this completion, it's also interesting that even though finite extensions of PA, they don't have the simplest model property, then PA in a sense can somehow impose on all its completions that they will still have the simplest model. And I'm interested whether, for example, it happens also for I sigma n's, or whether perhaps PA is the least such theory, whose all completions, I mean, in this language, whose all completions have the simplest model. So these are these kind of questions, and I will think exactly about this objection and this these examples of very complicated finite generated models. Thanks.
Other questions? Okay, I'll ask one. I think at one point you said that the countable recursively saturated models have rank omega plus 1.
So they have exactly rank omega plus 1. So, but it also follows from this reasoning,
right?
So
and is that is the converse of that? So if you are those the only ones that have rank omega plus 1? Is there a similar argument that you can make?
I think that these finitely generated models, they will have rank exactly omega plus 1, because you describe the type of the generator. And then you say that everything is definable from the element of this type, and this should do the job, and this should be omega plus 1.
Makes sense.
Sigma omega plus 1. Okay, so sorry. So each orbit is definable, right, with
no, but also I thought that the argument that you had for the recursively saturated case was really homogeneity. That having identical types implies being in the same orbit and a big equivalent. So if you take a homogeneous model that's not recursively saturated, you will also have rank omega plus 1.
Good point.
Okay. Any other questions? Okay, let's thank Mateusz again for an excellent talk.
Thank you. Thank you.
Thank you very much.
And I will remind you, we have one more talk scheduled for the semester next week at the same time. Karl Herbachik will be talking about something involving non-standard analysis. Recent results from Renling Jin. So it looks somewhat interesting. So please come back for that, and that will be our last one for this semester. Also, if anyone has any topics that they'd like to present, or has students who have topics that they would like to encourage the students to talk about, reach out to me and Norman, and we can schedule for the spring.
Right, and I just want to sort of follow up on what Atar said about Herbachik's talk. It is it's something quite sensational in a sense. This will be about Shemeredis theorem on arithmetic progressions. That's supposed to be a hard and difficult theorem in number theory, and then it's apparently Renling has a much simpler proof using non-standard analysis, for which he has this sort of construction of ultra products iterated 3 times, so 3 levels of non-standardness. And Herbachik will not give the whole proof, but he will discuss some axiomatic theories for non-standard analysis, where those levels of non-standardness are automatically built in, and makes those arguments. So you can do arguments like Shemeredis theorem in this setup, and then life becomes simpler. So it should be an attractive thing for everyone, not just for Mopians.
Okay, great. So we will see you all there next week.